Okay, let's dive in. If you've been exploring thermodynamics with us, you'll know we've already spent some time talking about enthalpy change. That's a delta H.
Yeah, delta H tells us about the heat, right? Positive if heat's absorbed endothermic.
Right, and negative if heat's released, exothermic.
And it's super important for tracking energy, absolutely. But, well, just knowing if something gets hotter or colder, that doesn't quite tell you if it's actually going to happen, like, on its own.
Exactly, that's the thing. Heat flow is, a big piece of the puzzle, but it's not the only piece when you're trying to figure out spontaneity.
Spontaneity, yeah. It's the key word. Will this thing just go without us needing to constantly, push it along?
And that's what we're digging into today. How do we predict that? How do we know if a process has this, built-in direction? The answer involves a couple more ideas, a couple more symbols.
We've got delta S, yes, for entropy change.
And delta G, drat G, for Gibbs Free Energy change.
That's it. And the material we're looking at today, it gives us the tools to understand these, and crucially, how they work together. How they give us this one powerful way to predict if something's spontaneous.
So we're moving beyond just the heat aspect.
Yeah, into randomness, probability, really the tendencies of the universe itself.
Wow, the universe. Okay, no pressure then. So our mission for this deep dive, really get to grips with delta S and delta G using our sources and, crack the code on spontaneity.
Sounds good. Let's start with that basic idea. Well, what is a spontaneous process?
Right.
Well, it's just something that occurs naturally. You leave the system alone, and it happens. It has a kind of preferred direction. No outside push needed once it gets going.
Like the examples in the source material, think about ice melting if you leave it out on the counter.
Exactly. At room temperature, anyway. Just go, turns into water.
You don't have to stand there making it melt. Or a waterfall, flows down, not up.
Gravity takes care of that one. Or steel rusting if you got air and water. It's spontaneous.
Okay, so that's spontaneous. What about the opposite, non-spontaneous?
That needs constant help. Continuous energy input, like pumping water up a hill.
Ah, yeah. You need a pump running all the time.
Turn off the pump. The water stops going up. Might even flow back down, which is spontaneous. So non-spontaneous things can happen, but only if you're actively driving them.
And this is where just looking at delta H, the heat change can fool you, right?
Totally.
Because you might think, okay, spontaneous things probably release energy, feel warm, exothermic, negative delta H.
That often helps, yeah. Exothermic reactions often are spontaneous.
But,
Ice melting. We keep coming back to that. It absorbs heat. Delta H is positive.
Yep, endothermic.
But above 0 Celsius, it definitely happens on its own. It's spontaneous. So clearly, delta H isn't the whole story. Something else must be driving it.
And that something else involves entropy, symbol S, and the change is delta S.
Entropy, often called disorder.
Right.
Randomness. Yeah, that's the usual description. Think about order versus disorder. A neat deck of cards, perfectly arranged, it's low entropy, very ordered.
Okay, then I knock it over. Cards everywhere.
High entropy, much more disordered, more random, lots more ways for the cards to be scattered than to be in that one specific ordered sequence.
Makes sense.
And a fundamental idea here is that systems, left to themselves, tend towards that state of greater disorder, greater randomness. It's just easier to be messy.
Tell me about it. My desk agrees.
Huh. Yeah, it takes work, directed effort to create order, to clean up the mess.
So systems naturally tend towards more entropy. What increases it? The source mentions temperature.
Definitely. Higher temperature usually means more energy, particles moving faster, more randomly. So yeah, entropy generally increases with temperature.
And changing state, like solid to liquid, liquid to gas.
Oh, huge jumps in entropy there. Solids are pretty ordered, right? Particles locked in place.
Yeah, like a crystal structure.
Liquids, they're moving around more freely, less order. And gases, particles are flying all over the place, totally chaotic. So S solid is much less than S liquid, which is much less than S gas. Big increases in disorder, so big positive delta S for melting or boiling.
Okay, that makes intuitive sense. What else? Dissolving things.
Often, yes. Especially if you take an ordered solid, like salt crystals, and dissolve it in water. The ions break apart, spread out through the water. You're going from a fixed lattice to dispersed ions. More randomness.
So increased entropy there, too.
Generally, yeah. Also, the complexity of the molecules themselves matters. Larger molecules or ones with more atoms tend to have higher entropy, just more ways for them to wiggle and vibrate and arrange themselves. Higher molar mass often correlates with higher entropy, too.
Got it. So delta S, the change in entropy, is like delta H. It's a state function, just final minus initial.
Exactly. Delta S equals S final minus S initial. So if delta S is positive, disorder increased. If delta S is negative, the system became more ordered.
And we can often predict the sign just by looking. Like, salt dissolving in water, gotta be positive delta S, right? More disorder.
You'd expect so, yes.
And steam condensing to liquid water, that's going from gas to liquid, more ordered. So, negative delta S.
That's right. Negative delta S for condensation.
Okay. And for chemical reactions, the source material says we can actually calculate the delta S for the reaction, delta S reaction.
Yep, delta S, Rxn naught if we're talking standard conditions. Just like with delta H, there are standard entropy values, S naught, listed in tables for different substances.
Ah, okay, so you use the balanced chemical equation.
Right. You take the sum of the standard entropies of all the products, multiplying each by its coefficient in the equation.
And subtract the sum of the standard entropies of all the reactants, also multiplied by their coefficients.
Exactly. Sum of products minus sum of reactants. The units are usually joules per Kelvin per mole. Notice the Kelvin in their temperatures involved.
Okay, so we can get a number for the change in system disorder, delta S system. So now we have delta H system, heat change, and delta S system, disorder change. But like we said with the ice, one might be favorable for spontaneity, the other unfavorable. How do we combine them?
This is where we need the big picture. The second law of thermodynamics.
The big one.
Yeah. And the way the material states it is pretty fundamental. All spontaneous processes occur in the direction that increases the total entropy of the universe.
Whoa, the universe? That sounds big. How on earth do we track the entropy of the entire universe?
Yeah, well, luckily we don't have to track the whole thing. For practical purposes, the universe is just our system plus its immediate surroundings. Everything else is too far away to be affected, usually.
Okay, that's a bit more manageable. So delta S universe equals delta S system plus delta S surroundings.
Exactly. And for a process to be spontaneous, that total delta S universe has to be positive, greater than 0.
So overall disorder must increase. Okay. We know how to get delta S system, maybe from tables, but how do we figure out delta S surroundings, the change in disorder outside our reaction?
Well, the surroundings are mainly affected by heat flowing in or out of the system, right?
Yeah, if the system releases heat, exothermic negative delta H system, the surroundings gain that heat.
And gaining heat increases the random motion of particles in the surroundings, increasing their entropy. So delta S surroundings will be positive.
And if the system absorbs heat, endothermic positive delta H system, the surroundings lose heat.
Right, which decreases their entropy, makes delta S surroundings negative.
So delta S surroundings is related to delta H system.
Directly. The heat gained by the surroundings is just minus delta H system. But the impact of that heat on entropy depends on the temperature.
How so?
Think about adding a bit of heat to something really cold versus something really hot. Adding, say, 100 joules of heat to something near absolute zero causes a huge relative increase in disorder. Adding the same 100 joules to something already boiling hot makes much less difference to its overall randomness.
Ah, okay. So the change in surroundings entropy is bigger if the heat is transferred at a lower temperature.
Exactly. The formula captures this. Delta S surroundings equals minus delta H system divided by T, the absolute temperature in Kelvin.
Got it. So delta S sur equals delta H syste.
That's the one. So now we can calculate delta S universe. We find delta S system, calculate delta S surroundings using delta H system and T, and add them together. If the total is positive, the process is spontaneous at that temperature.
Okay, that works. The source has examples of doing that math, but it still feels like two steps. Calculate system entropy change, calculate surroundings entropy change.
It is. And wouldn't it be nice to have a single value based just on the system that tells us about spontaneity?
That would be very nice. Is that where Gibbs Free Energy comes in? Delta G.
Precisely. Josiah Willard Gibbs came up with this concept. Gibbs Free Energy, G, combines the enthalpy and entropy of the system along with temperature into one function. The change, delta G, directly tells us about spontaneity.
Okay, this sounds like the key. What's the equation for delta G?
The fundamental relationship is delta G equals delta H minus T times delta S. That's delta H system and delta S system.
Delta G equals delta HT, delta S. And T must be in Kelvin.
Absolutely must be in Kelvin. Always use Kelvin in these thermodynamic equations.
Okay, so how does this delta G tell us if it's spontaneous? How does it connect back to that delta S universe zero rule?
It connects beautifully. When you substitute the expression for delta S surroundings, delta HT, into the delta S universe equation, delta S sys plus delta S sur 0, and do a little bit of algebra,
Okay.
you find out the delta G system is actually equal to minus T times delta S universe.
Whoa. Delta G equals T delta S universe. Okay, hold on.
So think about it. For a spontaneous process, we know delta S universe must be positive, right?
Right, second law.
And temperature T in Kelvin is always positive, so minus T is always negative.
Okay. A negative number, delta T, times a positive number, delta S universe.
Must give a negative result.
Which means delta G must be negative for a spontaneous process.
You got it. That's the magic of Gibbs Free Energy. It rolls the second law's criterion about the universe's entropy into a single value based only on the system's properties.
So the rules are simple then.
Very straightforward. If delta G is negative, 0, the process is spontaneous under those conditions. If delta G is positive, 0, the process is non-spontaneous, might happen in reverse. And if delta G is exactly 0,
Equilibrium.
perfect. The system's at equilibrium. No net tendency to go forward or backward.
That is so much cleaner. Just calculate one thing, delta G for the system, and, amazing. Now, the source talks about delta G naught, AG degrees. That little circle, standard conditions again.
Exactly. Standard Gibbs free energy change. Calculated when everything's in its standard state.
Which usually means 25 degrees C.
25 C, which is 298.15 Kelvin, yeah? And 1 bar pressure for gases, 1 molar concentration for solutions. That's the typical standard state.
So we can calculate delta G naught using the delta G equals delta HT delta S equation, just using the standard delta H naught and standard delta S naught values, and T equals 298.15 K.
Yep, that's one way.
Yeah.
Plug in the standard enthalpy change, the standard entropy change, and 298.15 K for T. Make sure your units match, though. Delta H is usually in kilojoules, delta S in joules per Kelvin.
Ah, good point. Need to convert joules to kilojoules or vice versa.
Right. Or there's another way, similar to calculating delta H naught reaction.
Using standard free energies of formation, delta GF naught.
Exactly. Tables list these delta GF naught values for many compounds. It's the free energy change when 1 mole of the compound is formed from its elements in their standard states.
And just like delta HF naught, the delta GF naught for a pure element in its standard state is 0.
Defined as 0, yes. Makes calculations easier.
So you do the same products minus reactants calculation, sum of delta GF naught of products times coefficients, minus sum of delta GF naught of reactants times coefficients.
That's the method. Gives you delta G naught for the reaction directly. The source shows examples using both approaches to find delta G naught and predict spontaneity at standard temperature.
Okay, but standard temperature is just one temperature, 25 C. What about other temperatures? That delta G equals the delta HT delta S equation has temperature right in it.
And that's key. Temperature plays a huge role, especially because of that T delta S term.
Let's go back to ice melting again. Delta H is positive, delta S is positive.
Right, so delta G equals positive delta HT,
Right.
positive delta S.
At low T, below 0 C, T is small, so T delta S is small. Positive delta H wins, delta G is positive.
Meaning non-spontaneous melting. Correct.
But at high T, above 0 C, T is larger. So T delta S becomes a bigger positive number. Eventually, it gets bigger than delta H.
So you have positive delta H minus a large positive T delta S. The result is negative delta G.
And negative delta G means spontaneous melting.
Exactly. Temperature flips the sign of delta G because of the competition between the delta H term and the T delta S term when they have the same sign.
And at the crossover point 0 C or 273 K, delta G is 0, equilibrium.
Right.
So you can find the temperature where spontaneity flips by setting delta G to 0, T is delta H, delta S.
Approximately, yes. Assuming delta H and delta S don't change much with temperature, which is often a reasonable first guess, the source shows calculating this crossover temperature for ice melting using the standard delta H and delta S values, and it comes up very close to 273 K.
That's really neat. It shows how the equation captures that real-world behavior. What about if delta H and delta S are both negative?
Okay, so delta H negative, exothermic favorable, delta S negative, more order unfavorable. Delta G equals negative delta H, T negative delta S.
That minus T times negative delta S becomes plus T delta S. So delta G is delta H plus T delta S.
Right. At low temperature, T is small, so the positive P delta S term is small. The negative delta H term dominates. Delta G is negative.
Spontaneous at low T, like maybe condensation, exothermic but more ordered.
Condensation is a good example. Spontaneous below the boiling point. But what happens at high T?
At high T, the positive T delta S term gets large. It could become bigger than the negative delta H term, making delta G positive overall.
Exactly. So non-spontaneous at high temperatures. Condensation doesn't happen spontaneously above the boiling point.
So the temperature dependence hinges on the signs of delta H and delta S.
Precisely. both positive.
Hmm.
Spontaneous at high T, non-spontaneous at low T, both negative. Spontaneous at low T, non-spontaneous at high T, delta H negative, delta S positive. Delta G is always negative. Spontaneous at all temperatures, delta H positive, delta S negative. Delta G is always positive. Non-spontaneous at all temperatures under those conditions.
That summary is really helpful. The source material gives other examples of calculating these crossover temperatures too.
It does. It really highlights how powerful the delta G equals delta HT delta S relationship is.
Now, there was one other thing mentioned briefly, coupled reactions, making something non-spontaneous happen.
Yes. Sometimes a process you want to happen has a positive delta G. It won't go on its own.
Like synthesizing a complex molecule in biology, maybe?
Often, yes. Those can require energy input. They're non-spontaneous. But nature is clever. It can couple that non-spontaneous reaction, positive delta G, with another reaction that is highly spontaneous, very negative delta G.
So you link them together somehow.
Mechanistically, yeah. So they happen together. If the negative delta G of the spontaneous driver reaction is larger in magnitude than the positive delta G of the reaction you want to run.
Then the overall delta G for the combined coupled process will be negative.
Exactly. The overall process becomes spontaneous. It's like using a downhill reaction to power an uphill one. Biology uses this constantly, often with ATP hydrolysis as the spontaneous driver reaction.
Fascinating. Like using a waterfall to turn a mill wheel that lifts something heavy.
Good analogy. The spontaneous process drives the non-spontaneous one.
Okay, wow. We've covered a lot of ground here. Let's try and summarize the key points from this deep dive.
All right. We started with spontaneity, things that just happen naturally.
And saw that delta H, enthalpy or heat change, isn't enough on its own to predict it.
Then came entropy, delta S, a measure of disorder or randomness, and the crucial second law. The universe's total entropy always increases in a spontaneous process. Delta S universe 0.
Which is system plus surroundings, but that was a bit cumbersome.
So we introduced Gibbs Free Energy, delta G. The star of the show, really. Delta G equals delta H minus T delta S, all for the system.
And the simple rule, if delta G is negative, it's spontaneous. If delta G is positive, non-spontaneous. If delta G is 0, equilibrium.
We saw how to calculate it, especially delta G not under standard conditions, using tables of delta H, delta S, or delta G formation values.
And we really explored how temperature, that T in the equation, is critical. It can determine whether something is spontaneous or not, especially if delta H and delta S pull in opposite directions thermodynamically but have the same sign mathematically.
Leading to crossover temperatures where spontaneity can flip.
And finally, the idea of coupling reactions, using a spontaneous one to drive a non-spontaneous one, making the overall process favorable.
So what's the big picture takeaway? It's that these concepts, enthalpy, entropy, free energy, they don't just describe the world, they give us predictive power.
Yeah, it's not just about observing what happens, but understanding why and predicting if it will happen under certain conditions.
And maybe even how to make it happen, or stop it from happening by playing with those conditions, especially temperature.
Right. Controlling temperature or coupling reactions, these are ways we can influence spontaneity. Think about refrigeration, preventing food spoilage, a spontaneous process, by lowering T or industrial synthesis.
So the final thought to leave you with is this. How does this fundamental predictability, this ability to know if something will go based on delta G, shape the world? From water freezing to chemical plants operating to life itself functioning.
Yeah, start looking around for examples. What processes do you see happening effortlessly? Those are likely spontaneous, driven by a negative delta G. What things require constant energy input? Those are non-spontaneous. Think about the delta H and delta S involved. It really is everywhere.